emitter base, which is in forward bias, and collector base, which is in reverse bias. That is an active base or active region of its characteristics. So that which can be establishing a quotient operating point, that you can call it as a Q. So in this region, active region, so that it is necessary to apply an appropriate direct potential as well as the currents. So when signal is not going to be applied to the base here, the collector current and voltage, which may be determine a point approximately in the center of the output characteristics. So you need to remember that if signal is not going to be applied to the base, collector current and as well as the voltage, which is going to be determining a point approximately at the center of the output characteristics. Center of the output character. That means input as well as the output characteristics. With the zero base excitation, the operating point I, which is called as quotient point capital Q. Okay. So this is very, very important. That means biasing is the procedure which may be established and as well as which can maintain a quotient operating point of the circuit. So transistor current components. So we know pretty well here, transistor means which may have three regions: emitter base and collector region. So emitter base, which is always in forward bias, and the collector base, which is always in reverse bias, and emitter region, which is always in highly doped region, and collector is moderately, and base region is less, and the base, which is a thinner layer compared to that of the emitter as well as the collector region. So this you know already here. NPN transistor is to be considered here, so that the DC supply which is to be applied to the NPN transistor. That means that's that you should follow the here conditions of the transistor here. Emitter base, which is always forward bias, means here. NPN transistor, N means N type of semiconductor material, positive, negative electrons are the majority charge carriers. So that negative charge. So that the DC supply negative terminal. So that if it is going to be connecting negative terminal of the battery, which is connected to the N type semiconductor material, that is in forward bias. Similarly, in collector region, collector base region, which has to maintain a reverse bias, means here negative electrons as well as the DC supply positive terminal of the battery, which is connected to the N region. That is always the charge carriers which are attracted toward the battery positive terminal in the collector region. That means a reverse bias. But whereas in the case of collector base, which are repelled, why? Because of negative electrons, negative charge, there should be a repulsive forces to be takes place. That's why easily the charge carriers which can move from the one region into the another region. That is the case. You need to know about this. Okay. So emitter, which may have emitter current due to the electrons, is IE, and hole current, which you can call it as a IPE. So that positive holes, emitter region, which may constitute the current, is IPE. Negative electrons, which may be constituted in the emitter region, is INE. So the ratio of the holes to the electrons current crossing the emitter junction, which is always proportional to the ratio of the conductivity of the P type to N type material. Okay. So, and also in practice, by doping, emitter is made much larger than the doping of the base. Okay, why? Because of these can be utilized, which can be easily moved from emitter into the base region across the emitter diode, that or else you need to say that emitter base junction. So that this which is going to be ensuring that emitter current is entirely due to majority charge carriers. Okay. If 100% of the majority charge carriers which is coming from the emitter region, which are entering into the base region across the emitter base junction or the emitter diode, so that there a minority charge carriers which are available here. So here in this condition. So N material which is having majority negative electrons, P is having majority positive holes. Whenever 100% of electrons which are coming and crossing this junction and enter into the base region, there only those are going to be combining with the majority with the minority, and remaining 98 to 90%, 95% of the majority charge carriers which can repel, that means inject toward the collector region across the collector diode or else the collector base junction here. So that this is the condition here. So here a minority current which is to be constituted at the base region. So that what is the current which is to be constituted at the base region? That is IB. Okay. So base current here. That is the minority charge carriers. Okay. Which is to be constituted the current here. So this is the case wherever you to be considered here, whether it is NPN or PNP transistor, the same thing will follows here. So what is the total collector current here? Okay, so that is also to be calculated. So here hence the total minority carriers current, which is I equals to IPN with plus INP here. So not all the majority carriers which may cross the emitter base junction. Just now I already told you JE. Okay, and emitter diode, emitter junction here, and the base collector junction. So some of the which are combined with the majority charge carriers, and just now already discussed all these points here. So what is the total collector current under this emitter junction which is in forward bias? So ICO minus plus alpha E, and also for NPN transistor is also okay. So what total collector current which may be giving in this equation. So like that here, whether if you consider whether PNP or NPN, whatever it may be here, the same maybe follows here concept. Okay. Next, thermal runaway. Thermal means temperature related here. So which is going to be operates separate batteries for biasing a transistor. So and also which is expensive and inconvenient. Why? Because of it here, which may provide the bias voltage from a single source of power supply. So, so to understand the design of these circuits, which may be called biasing circuits, and it is necessary to understand clearly the current flow in the transistor here. So let us consider that this figure, which is going to be showing that here, which is a NPN transistor. So the emitter current is IE, and which is the sum of the base current, that is IB, and alpha IB. Okay, so which is coming and entering into the collector region, which may comes from the emitter to the collector across the base region. So in spite of the reverse bias, there is a collector base current ICO, which is caused the thermally generated minority charge carriers. In ICBO means collector to base with emitter open here. So if no current which is passing in the emitter region, so that the charge carriers which can move from the collector to the base due to the minority charge carriers. That is the case. IC equals to alpha IB plus ICBO. Okay. So here stability factor, that is DIC by DICO. That is the stability factor here. So here ICO which may tends to develop a bias on the base, and which may increases the emitter to collector current in the transistor. So when base is open, that means there cannot be any net base current due to the minority charge carriers. So here the collector current which may be increases the temperature of the transistor. So this increase ICBO with in terms of increase the IC value, collector current value. This process goes on cumulatively, and a large current which may be built up, which finally may damage the transistor here. A more current which is to be accumulated at the collector region, so that is going to be damage the transistor. So this phenomena which is called as a thermal runaway. That means to prevent the thermal runaway, the biasing circuit should be designed properly, and increase in temperature should automatically lead to decrease the base current, and such that collector current should get constant. Okay. So if the change in the collector current with respect to the change in the minority charge carriers collector to base, which is called stability factor. Most important short question is that. Next is the fixed bias arrangement. This is the circuit diagram. A transistor is to be considered. So here, toward the emitter, which is coming out here, NPN transistor is. So here, the method, a method of biasing the transistor, which is also known as current biasing, fixed biasing, which is also known as current biasing. So in this circuit, a quotient base and collector current, which are supplied by a single power supply, VCC here. So it biases the emitter base junction, which is biasing emitter base junction in the forward direction, and the collector base which is in reverse bias. Okay. So the voltage, base emitter voltage will be in millivolt range, 10 power minus 3, and which can be neglected in compared to the VCC. So what is the bias current here? IB is VCC minus VBE by RB. Why? Because of I equals to V by R. So that's what here, VCC by RB. Why? Because of VB is, which is much lesser than that of the VCC. That's why we are neglecting VB, base emitter voltage. So remaining is VCC by base resistance RB. So here where the current is constant, so that this circuit is called fixed bias. Substituting these equations, IC equals to total collector current, that is beta IB, that is alpha by 1 minus alpha into IB plus IC by over 1 minus alpha. So stability factor, which is giving out. So for stability factor is for 50, for alpha value is 0.98, which is indicating that the collector current which may be increases 50 times faster than the minority current. So that this circuit does not provide a stability operating point. Okay, this is the fixed bias circuit. What about the self bias or the emitter bias arrangement? So self bias, which may provides a sufficient protection from thermal runaway. Okay, if more current which is accumulated in the collector region, so that there the transistor is going to be damaged, that is due to the thermal runaway. So here, to protect from the thermal runaway, the resistors here R1, R2, and emitter resistance RE, and load resistance is RL. Okay, and supply VCC, which are provide appropriate bias voltage and currents, R1, R2, RE, RL. This is the transistor. Okay. So the collector current IC here, which may develops the voltage drop across RL. So this is a collector base emitter. So this is a common emitter circuit here. Configuration. So collectors are current IC which develops a voltage drop across the Y because of here IC is there, RL there. Okay. So V equals to IR means I equals to V by C, V by I. So here IC which may develops the uh, emitter resistance with the emitter side as a positive and RE here. Voltage drop across the RE with the emitter side as a positive. When the collector current increases due to the rise in temperature, the voltage drop across RE increases, which makes base terminals less positive. This decrease base current and again which in turns decrease with the collector current. Okay, that means whenever the collector current which is going to be increasing with due to the temperature here, voltage drop across the RE which is also increases. Okay, so that means a base which is a less positive. So if it is a less positive means there is a decrease in the base current again which may turns into the decrease the collector current here. So here the self bias circuit which is similar to adopt the fixed bias circuit. The two resistors R1 and R2 here, R1 and R2, the base circuit which may constitute the voltage divider, the voltage source VCC and R1 and R2 which may be replaced by the Thevenin's equivalent circuit here. Okay, self biasing. So that what is the Thevenin voltage? By applying the Kirchhoff laws, you can easily calculate the what is the base current as well as substituting in collector current alpha by 1 minus alpha into IB. IB is this one plus ICB by 1 minus alpha. So by simplifying, you will get this equation and the stability factor DIC by DICB. You can easily calculate. For a good stability for emitter resistance by base resistance ratio, which is more which is far less than that of the one here, then stability factor which may be a good stability. Next, BJT as an amplifier. So here the what do you say here? A transistor can be used as an amplifier. Okay, amplifier means a transistor strengthen the signal. That means whenever weak signal which is coming out here, by using a transistor which may fed through the transistor means which may be strengthen the signal here. Weak may be converted into a strong signal here. Okay, so that is due to by an amplifier for time varying signals. Taking a specific example. So the characteristics of NPN transistor to be used as an amplifier. So here the bias circuit used previously and the values already we already known. Base emitter voltage which is negligible. What is the question point here? That is IB value VCC by RB. Why? Because of VBE which is negligible. So like that we can easily. So here VC and IC value. So small variation of the base emitter voltage here. Variation is to be observed. Whereas the collector large variation in VCE. So here where do you observe? That is to be referred. So what is the expected question is describe the fixed and self-bias statements. Locate the quotient operating point of transistor. Okay. Next is the introduction to the amplifier. So what do you mean by amplification? Amplification is the most common process that one comes across in electronic circuit. An amplifier is a circuit which raises the level of a signal. Just now we discussed that. A small signal which may be processed through the input here, which may provide the output with an identical to the input to all the respect, except that it is a larger in magnitude. That means strengthen the signal. Amplification accomplished by controlling of a power supply with an element that is actuated by the signal to be amplified. So, what are the thermionic values, the transistors, which are the common control elements which may be used here? Working of an amplifier. IP means input signal, OP means output signal here. Okay. So RL is the load resistance here. And here PS is the power supply. This is a DC supply. This is an AC supply here. Okay. And this is the ground. C control element, amplifier, control element. Okay. So the amplifier can be thought of in a black box, which has a 2 input terminals, 2 output terminals, and a terminal for supplying a DC power. When the signal is to be amplified means DC or AC, that is a voltage or current. So it delivers some power to the load. Across the load only we are taking the output here. Okay. So here the output power which may be derived from the DC power supply, not from the signal source, AC. So a part of the output of an amplifier which may be fed through the stabilize its performance by using feedback. The gain of the amplifier can be made much greater than or more stable or less sensitive to change. So we have to know about that what is the feedback concept regarding to the negative as well as the positive feedback. So classification of amplifiers, but that is the circuit which may be used in amplifier which can depends on the nature of the signal is to be amplified and the amount of amplification, how much the signal can be amplified. Okay. So that here amplifier circuit which may be classified on the based on these factors, and many different classifications which are also possible. So classification based on the transfer function means here the relation between the output and input of an amplifier, which is called the transfer function, output and input. So the input to an amplifier may be VI, VI is input voltage, or else input current is II. Similarly, output voltage may be V0 and output current is I0. So that there should be a 4 possible combination of input as well as the output signals. So there are hence 4 types of amplifiers are possible. The 4 types of amplifiers which may be here. What is that? The voltage type means we gain output voltage by input voltage, V0 by Vi. Current, output current is a gain, AA equals to I0 by II. Transconductance, GM equals to I0 by Vi. Trans resistance, Rm equals to V0 by II. Okay, R equals to V by I. We know that. That's why here output voltage by input current. So here classification based on the method or analysis. So it is normally assumed that the gain of amplifier does not depend upon the amplitude of the input signal. And here It is true that the amplifier is operated on a linear part of its characteristics. Such amplifiers, you can call it as a linear amplifier. So here, for example, amplifier gains 100 and input voltage 5 millivolts, output voltage is 0.5 volts. The same amplifier of the input voltage is 50 millivolts and output is 5 volts. So this amplifier, which you can call it as a small signal amplifier. That means signal is small enough to confine the operation of the linear part of the characteristics. Okay. Whereas in the case of a large signal amplifier, the input signal is so large and the device does not operate the linear part of the characteristics. Okay. So classification based on the frequency range. Say signal amplifier cannot amplify signals from direct current DC to very high frequencies. So each amplifier caters to a particular limited frequency range. The classification frequency range of amplification DC to LF, that is amplifies DC and low frequency signals only. DC signal is only going to be amplified at low frequency signals. Next, audio frequency, that is 20 to 20 kilohertz. Radio frequency 20 kilohertz to 300. Okay, a video that is with a very wide band width, that is amplify signals from video camera. Next is the classification based on the types of coupling one to each other. So a amplification which may be provided by a single stage amplifier which is not sufficient. So there only we are using another one. Consequently, 2 or more stages. Where do you observe in the case of RC coupled amplifiers? Okay. So there is a strengthen the signal. Whenever if you by using a single stage at input stage input, if you give a 1 voltage, the output may be 2.5 like that. Okay, again another stage is to be considered. That means here the output of the first stage which is fed through the input of the second stage. Then if you consider if you taking the output at a second stage, there only the signal or the voltage or a current maybe increases gradually. Okay, if it is giving 2 voltage, there may be 3.5 or 4 volts like that. So that that is cascade. Okay, cascaded. So that in such systems, the output of one stage is connected to the input of the next stage, which is called coupling yes, network. So how the cascading is to be takes place between the two stages. You can easily observe that here V1 is a input voltage, A1 is amplified here. Again, the output is V2, which is connecting to this input of the second stage. So that what is the signal finally. Okay, you can observe. So this interstage coupling may be achieved by RC. Just now we discussed that RC, resistance capacitance network, RC network or a transformer. So the network couples the AC signal and decouples the DC voltages. Please remember this. Coupling the AC and decouples the DC. So here to amplify the DC voltage, the coupling has to direct one. So based on this consideration, we have to direct coupled, resistance capacitance coupled, and transformer coupled amplifiers. So here classification based on the conduction angle. So amplifiers may be classified on the basis of the conduction angle during which output current flows. Class A amplifiers have output signals during the complete input cycle. So all linear and some power amplifiers are operated under this case. Okay. So in class B, the signal current flows for 180 degrees. The signal current flows 180 degrees of the cycle. Okay. So this is the input signal here. So 0 to pi means 180 degrees, pi to 2 pi 360 degrees. So here you can able to observe this case. Okay. So the signal current which may flows 180 degrees of the cycle. Whereas in class C, this is class A, this is class B, this is class C. Okay. So here the output which is present only for less than the half input cycle. Half input cycle. In the case of what do you say? Class C amplifiers. Usually, which has tuned a circuit to the load. It is characterized by high efficiency. It is amplification included radio and television transfer. Okay. This is the gap between class B. This is class A, B, and class C. 1 minute. So you can see here class A and class B power amplifiers. You can see class A which has a high linearity and low efficiency. This is the class A, 0 to T and T to 2T. Okay. Whereas in the class B is a high efficiency. In class A is a high linearity. Class B is high efficiency. Class B is high efficiency and low linear. See here. This is the case. Here also. Okay. High efficiency, low linear. Here in class A, high linearity, low efficiency. Whereas in the case of class AB, both, you can able to observe. Compromises between class A and yeah. Okay, is it clear? So I have been show the circuit different cases for amplification, amplifiers, class A, class B. This is the class C. Next, amplifier parameters. Some of the parameters that may be characterizes the behavior of the amplifier. This is the another essay question here. Voltage gain, AV. So the ratio of the output voltage to the input voltage. AV naught by VI, that is nothing but AV, voltage gain, So it may be measured the feeding of a signal for a particular frequency to the amplifier and measuring the output voltage. So this is the signal voltage resistor and amplifier. Vs is the source signal output voltage across the load resistance. Okay, so input current and output current here. So here current gain AI, output current by input current is nothing but a AI. So what is the normalization, normalized gain? A by A maximum. Next, power gain. P equals to V square by RL. That is which AV by AI is nothing but a power gain. That is voltage gain by here current gain ratio, which may be given here power. Okay, V square RL. Input resistance. What is the input resistance? According to the Ohm's law, Ra equals to Vi by Ia. Output resistance. Next, efficiency of the amplifier. So the power amplifier which may convert the DC power into signal. Okay, DC power into signal here. So the efficiency of the amplifier, eta equals to RMS value of the signal power by DC. Okay, that is the efficiency. Next is the frequency response. You can see here the bandwidth here. Okay, so at what range the frequency response of an amplifier? The mid frequency range. What is the higher frequency? At lower frequency, how it is going to be increasing the gain value, and at mid frequency stability. At higher frequencies, again it is going to be dropping here. So the bandwidth, which may be the difference between the higher frequencies to the lower frequencies, bandwidth. Next, gain of an amplifier with negative feedback. So this is the feedback circuit here. So this is an amplifier, feedback circuit. This is the signal source, whereas this is the input voltage, this is the output voltage. A fraction of the output which may fed through the feedback circuit and into the input, whether the strength of the signal may be increased or decreased. Okay, that you can call it as an amplifier. If it is going to be increasing positive, if it is going to be decreasing negative. Okay, now. So what is the beta feedback amplifier ratio? What is VF value? What is the AF value? Gain with feedback, AF. That is A naught by 1 plus beta A naught. You need to do the calculation part. Beta A naught. What are the effects of the negative feedback here? Gain stabilization and reduction of the distortion, noise reduction, improvement of the bandwidth here compared to the previous one, and effect on input as well as the output impedances. Okay. Next is the emitter follower or common collector. So emitter follower. So signal, and this is the base, and this is the collector here. This is the emitter here across this load resistance. This is VCC. Across the load we are taking. This is the ground. So emitter equivalent to the emitter follower circuit. So both are same. Emitter follower equivalent circuit. Here the voltage, output voltage, V0 is developed across the load resistance, which is connected to the emitter in previous section here. So the entire voltage V0, which is feedback in series with the input signal. This one, output. So the voltage feedback VF, which is equals to the output. So that is beta. So it may be also noted that effective input signal, which is applied to the resistor and transistor, which is equals to the difference between the external applied voltage, signal voltage, and the out V0, Vs minus V0. Here, what is the gain? Current gain, I0 by I, input resistance, and here voltage gain, AV value, output impedance. Distinguish between class A DC amplifier. This is the case. There's so many times this question is asked as a essay question. Different methods of classifying amplifiers. Next is a common emitter amplifier. So transistor circuits, amplifier circuits, classified according to the element of a device common to the input and output circuits. The three possible configuration of common emitter, common base, common collector. That means whenever if you want to operate this three terminal transistor in circuit, input it is needed two terminals, as the output it is needed two. Total is four, but it is having only three. So that out of these three, one is common for input and output. Then you can utilize in circuits. So that's why if emitter is common for input and output, then that is called common emitter configuration. Similarly, base also and collector also. So here is common emitter amplifier is the most popular configuration. So what is single stage BJT? A common emitter amplifier, single stage common emitter amplifier, which is having a resistors R1, R2, RE, RE, which are bias resistors, which need to set up an appropriate operating point. Capacitors, CT and CZ are called coupling capacitors, and they block the DC direct current and prevent the DC from entering the signal source to the load. So the capacitor C is called the bypass capacitor, and RE is short circuit RE at signal. So here, what are the conditions means here? So this is the case. Single stage BC. So RE, and this is here only we are taking. We are giving input. We are taking out. Okay. This is NPN transistor. R1 and R2. RL and RE. RE is the emitter diode. resistance, load resistance. This is C2 is the coupling capacity. So here the to transfer all components, that is resistor, capacitor, and signal source from the actual circuit to the equivalent circuit. There is a change in from the Q point and replace each independent DC source by its internal resistance. The ideal voltage source which is replaced by the short circuit. Applying the Kirchhoff rules, this linear circuit. So two-port representation of a transistor. Input voltage, output. This is a two-port. BB means black box. One is input port, two is output port. So H parameters, hybrid. How the input characteristics of a BJT is going to be changing. What are the OP characteristics, output characteristics of the BJT? So hybrid parameters is H11, H12, H21, H22. These are the hybrid parameters. So equivalent circuit of a transistor with respect to the H parameters. This one. So this is the CA amplifier, common emitter. How it is going to be amplifying the signal. So what is the current gain, input resistance, output resistance, voltage value. Next is the frequency response of common emitter amp. For an amplifier, the frequency characteristics may be divided into three regions. One is the range of the frequency, which is called mid band frequencies, over which the gain is constant. Gain means output voltage by input voltage. The characteristics which may be obtained by ignoring the capacitance belongings to mid band of classification. So here the coupling capacitor, which may plays an important role in decreasing the gain. So the input signal which is given to the potential division network consisting blocking capacitor and input resistance of the amp. LF means low frequency range, MF means mid frequency range, and HF means high frequency range. Okay. So that the frequency, if it is going to be decreasing from the mid frequency range, and the capacitance reactance, capacitive reactance goes on increasing. As a consequence, more and more voltage is dropped across the blocking capacitor. Here. So you can able to observe. At the lower frequency range, normalization of the gain with respect to frequency on x-axis. Frequency versus gain. So this is a high frequency range. This is the mid frequency range. Constant values. These are the questions. So you can see that model questions. Draw the circuit diagram of common emitter amp. So we have been discussed so many circuits based on the concept. The thing is that you need to practice. How you can remember this? Means basics through PPT. I have been explained all this. Previous class. Go through the previous class. So there only you can able to find out that how to design a circuit. What are the conditions you may follow? Okay. So then only you can able to understand. Without having the practical knowledge, you cannot survive. So here draw the circuit diagram of a common emitter amplifier and explain its working, how it works. So in this conditions also you need to write it down and draw the equivalent circuit of the common emitter amplifier and what are the characteristics parameters, output, gain, what do you say, gain voltage, gain current, current gain, current voltage, uh, uh, and also here everything. 4 or 5 conditions are there. Based on that, you have to discuss. And also maybe a short questions from the BJT, how the BJT maybe works as an amplifier, and the frequency response of a common emitter amplifier. So 3 different regions: common emitter, low frequency range, high frequency, and mid frequency range. Okay. Only the thing is that you have to know about the RC coupled amplifier. If you know the RC coupled amplifier circuit, there only we are using NPN transistor with common emitter configuration. Emitter is common for input as well as the output. So that based on that only, we are deriving the answers from equations from that. Okay. So that you can achieve by doing the practice at least twice or thrice. If you draw the circuit, you can easily remember. And here also, what is the equivalent circuit diagram for the here the common emitter amplifier? Okay. What about the H parameters? Hybrid parameters. H parameter means hybrid parameters. So that is also you need to practice. H11, what is H11 value? H12, H21, H22 values. All these you need to do practice. So here the thing is that you can go for this in previous, what is class A and what is class B and class C amplifiers based on these. So by coming class, next week we will go for power amplifiers. Okay. To PPT I will explain you. So in this power amplifier, what is fixing the quotient to operating point, what is class A power amplifier. Okay. So how you can direct coupled load and transformer coupled load, differences between these two, what is push-pull amplifier, like that. Okay, na? So right, all the best. Coming class we will discuss the next course. Right, thank you all.